Hello everyone, in this video we're going to discuss the paper FlexiViT, One Model for All Patch Sizes, which is a paper by Google Research. Vision transformers work by slicing images into patches, and patch size controls a trade-off between speed and accuracy, with smaller patches leading to higher accuracy at a greater computational cost. However, changing a patch size for a model requires retraining a model. In this paper, the authors show that by a simple change, such as randomizing the patch sizes at training time, we can obtain a single model that performs well across a variety of patch sizes. This means that we can tailor a model for a given compute budget at deployment time. The authors compare the performance of the FlexiViT model to standard ViT models in a variety of computer vision tasks, such as classification, image text retrieval, open world detection, panoptic segmentation, and semantic segmentation. And they show that their model matches or outperforms standard ViT models' performances. We can understand more about how FlexiViT works if we look at the overview figure on the left. The same image can be sliced into a different number of patches. And in both cases, the patch embedding weights are resized on the fly to match the patch size. The resulting image tokens are then fed into a model that shares the weights for all patch sizes. On the right, we see a comparison of the validation performance between FlexiViT base, ViT base 16, and ViT base 30. On the x-axis, we see a sequence length at inference time and the patch size, and on the y-axis, we see precision for ImageNet 21K. And we see clearly that FlexiViT base performs well across a variety of patch sizes, while ViT base 16 and ViT base 30 both have peaks at the corresponding patch size on which they are trained. Beyond that patch size, we see that the performance degrades very quickly for both vision transformers. So how does FlexiViT achieve the superior performance? On the left, we see a pseudo implementation where the changes required to make the training of a ViT flexible highlighted in purple. First, we choose an underlying parameter shape. Here it's 32 by 32 for the embedding weights and 7 by 7 for the positional embeddings. At each iteration, we choose a patch size at random from a uniform distribution in the range of 8 to 48. Then with the randomly chosen patch size, we resize the embedding weights and the positional embeddings. But how do we resize the patch embeddings? The figure on the right shows that the PI resize or pseudo-inverse resize method proposed by the authors perform better than other methods. A straightforward way to resize the patch embeddings would be to use bilinear interpolation. However, this has the issue that the resulting magnitudes for different patch sizes are also very different. To solve this problem, the authors formulate an optimization problem to minimize the square of the difference between the dot product of the patch and the embedding weights and the dot product, the resized patch, and the new resized embedding weights. They show that the optimal solution in this case is the pseudo-inverse of the bilinear resize operation matrix. And in the case of downsampling, they make an assumption about the probability distribution of the patches in order to find the optimal solution. And in this case, the optimal solution is also the pseudo-inverse of the bilinear resize operation. And as we can see from the figure, this approach performs better, especially for the upscaling case. As we see in the other methods, the degradation in the performance in the upscaling case is much worse than the pseudo-inverse method. Next, the authors use knowledge distillation to train the FlexiViT. They choose a ViT base 8 model as a teacher model, and they use a FlexiViT as a student model. In this figure, we see a comparison of the performance for the teacher initialization, a random initialization, and a training that is supervised with labels and no distillation. The teacher initialization is shown in green, and the random initialization, no distillation are shown in red. We can see that for a teacher initialization, FlexiViT student matches the teacher for the smaller patch sizes. We can also see that compared to the random initialization and no distillation, teacher initialization achieves significant benefit. The different green curves show the different lengths or epochs for which the training takes place. The dark green curve is training for 90 epochs. The two pale green curves are for 300 and 1,000 epochs. In this figure, the authors compare the performance of FlexiViT base to ViT base 30 and ViT base 16 after fine-tuning for a variety of computer vision tasks. Here, FlexiViT base is fine-tuned at each of the target patch sizes 30 and 16, and then its performance is compared to the standard ViT at each patch size. We can see the performance for classification, panoptic segmentation, open vocabulary detection, blocked image tuning, as well as semantic segmentation. FlexiViT base outperforms the standard ViTs at the smaller patch sizes consistently, while it matches or does slightly worse at the large patch sizes. The bottom figure shows resource-efficient transfer for FlexiViT. The authors show that flexibility of a FlexiViT model is retained even after transfer at a fixed patch size. We can exploit this property to get a boost in performance at no cost if we transfer learn at a large patch size and use a small patch size at test time. We see in the figures here the x-axis represents the input grid size at test time, and the y-axis represents ImageNet accuracy. For the left figure, we see FlexiViT base, which is fine-tuned at an 8x8 grid, and a standard ViT base 30, which is fine-tuned also at an 8x8 grid. We see that for FlexiViT, as the input grid size increases, we get a boost in performance, whereas for the standard ViT base 30, we see a dip in performance as the input grid size increases. On the right side, we see FlexiViT models that are trained at 8x8, 15x15, and 30x30 for fine-tuning, and then we see their performance for different input grid size at test time. For all the three models, we see that as the input grid size increases, or as the patch size decreases, we get a boost in performance, even though we trained very cheaply during transfer learning at a larger patch size. On the leftmost figure, we can see another interesting result. Here we are looking at flexifying models that were pre-trained using standard vision transformers without flexibility. In this case, we trained the models with flexibility during fine-tuning. Particularly, if we look at the ViT base 30 and ViT base 16 in orange and olive green, we see that the performance without flexibility during pre-training or fine-tuning, which is given by the horizontal bar, is very close to the performance when flexifying these standard models during the fine-tuning phase. In some cases, flexifying the model will outperform standard fine-tuning, and in other cases, standard fine-tuning is slightly better. On the right bar, we see the performance for FlexiViT base, which uses flexibility both during pre-training and fine-tuning. The middle figures here show the performance for different tasks using FlexiViT. Here on the left, we see LIT, which is an image text model trained with and without flexibility, and we see a similar trend using FlexiLIT, which performs well over a variety of patch sizes, compared to the LIT-VIT, which are trained without flexibility. We see a peak in performance for a specific patch size, and then the performance degrades quickly at larger or smaller patch sizes. On the right, we see a similar trend for a task of detection in images. For models with standard VITs, we also see a peak in performance for the target patch size, while for the FlexiViT, we see a good performance throughout a range of patch sizes. And then lastly, we are looking at how FlexiViT, or the use of flexibility, can improve the speed in pre-training. By specifying a curriculum, which is a sequence of probability distributions over the patch sizes, we can pre-train a fixed VIT faster. For a desired patch size, we choose the last probability distribution in the sequence such that it places its entire mass on set patch size. We can see that using such a scheme allows us to achieve the same performance as standard pre-training of VIT base 16, only much faster. Here, the authors ask the question of whether FlexiViT processes inputs with different patch sizes in a similar way. To do this, they analyze FlexiViT's internal representations. On the top left figure, we look at centered kernel alignment, and we see the different colors representing the different blocks in FlexiViT, and the dot size represents the grid size. We see the dots of different size but same color clustered together, indicating that FlexiViT handles the different patch sizes similarly. However, this trend goes only until block 6. Beyond that, we see the representations diverge for the different grid sizes. At the end, or toward the deeper blocks, we can see that the representations converge again for the different patch sizes. On the bottom left, we see a slightly different trend for CLS tokens. Here we see the cosine similarity between CLS tokens for different grid sizes for different blocks of FlexiViT, and we see that representations from different blocks consistently cluster together irrespective of the grid size. On the top right, we see an example of relevance maps for VIT base and FlexiViT base. Here we can observe that attention changes significantly at different scales. We can see that as we decrease the patch size, the attention relevance concentrates into a larger number of smaller areas throughout the image. On the bottom right, we see the relation between token representations across different scales. For these 4 figures, we are looking at the cosine similarity between a seed token at a patch size of 16 and other tokens on the same patch size as well as in different patch sizes or different scales. From these figures, we are able to see the correspondence between tokens across different scales. To summarize, the authors show that FlexiViT, where they make a simple change during training, that is randomizing the patch sizes of the input image, can give us one single model that performs well at test time across different patch sizes. This model is compared to existing standard vision transformer models and shows that it does well on a variety of different computer vision tasks. Please subscribe to get notifications when we post new videos. Thank you for watching.